instruments like camera, projector, microscope, binoculars, telescope, etc. have drastically widened the view of the world. Eyeglasses allow the people to see and read in comfort. Do you know which optical component makes all these possible? It is simply a lens. A lens is a transparent material bound by two surfaces, out of which at least one surface is spherical. A lens having both spherical surfaces bulging outward is a convex lens or double convex lens. It is thicker in the middle than at the edges. This lens can converge light incident on it. Have a look at the figure. So, it is a converging lens. A lens having both surfaces curved inwards is a concave lens or double concave lens. It is thicker at the edges than at the middle. This lens can diverge light rays incident on it. Have a look at the figure. So, it is a diverging lens. Concepts related to lens. Each lens has two spherical surfaces. Each of these surfaces forms a part of a sphere. Center of curvature C. It is the center of the imagery sphere which forms the given lens. Each lens has two center of curvatures C1 and C2 respectively. Principal axis. It is an imaginary straight line passing through the two centers of curvatures of lens. Principal axis is perpendicular to the surfaces of the lens. The effective diameter of spherical lens is called the aperture of the lens. It determines the amount of light passes through the lens. Optical center O. The central point of lens on the principal axis is its optical center. When a ray of light passes through the optical center of a lens, it passes without undergoing any deviation. A convex lens may be thought of as an arrangement of number of triangular prisms with very thin glass slab in the center. Base of each prism points towards the principal axis. We know that when ray of light is incident on prism, it bends towards its edge and then emerges out. Do you know, when beam of light parallel to principal axis strikes the lens, rays will undergo refraction as they enter the lens and then leave the lens. First they bend towards the respective prisms and they emerge bending towards the principal axis. That is, they converge at a point of principal axis. It is called principal focus of lens and denoted by F. The distance between focus and optical center is called focal length. Principal focus of convex lens F. When several rays of light parallel to principal axis are incident on a convex lens, they converge at a point on a principal axis. It is the principal focus on the convex lens. Every lens has two principal foci. Focal length small f. The distance between principal focus and optical center of the lens is the focal length. To determine focal length of a convex lens. Activity. Take a convex lens. Place it between the screen and distant object like a tree in a building. Move the lens towards or away from the screen till you get a well-defined image on the screen. Can you guess at which point you get the image? Measure the distance between the screen and the lens. Image of a distant object is obtained nearly at the focus of the lens. So, in the above activity, the distance between the screen and the lens is the focal length of the lens. Image is formed by a convex lens. Activity. Take a convex lens. Determine its focal length as per the previous activity. Draw 5 parallel straight lines on a long table such that the distance between the successive lines is equal to focal length of the lens. Place the lens on a lens stand. Place it on the central line such that optical center of the lens lies just over the line. The two lines on either sides of the lens correspond to F and 2F of the lens respectively. Mark them with appropriate letters 2F1, F1, O, F2, 2F2 respectively. Place a burning candle in different positions on one side of the lens. 1. Far beyond 2F1 to the left. 2. Just behind 2F1. 3. At 2F1. 4. Between F1 and 2F1. 5. At F1. 6. Between F1 and O. Every time, obtain a clear, sharp image on opposite side of the lens. Record the position, relative size, and nature of the image and verify it with the table. Rules for obtaining images. Images formed by a convex lens can be studied with the help of ray diagrams. Ray diagrams are useful to study the position, relative size, and nature of the image formed by lenses. Following are the rules for obtaining images by convex lens. Rule 1. If the incident ray is parallel to principal axis, then the refracted ray passes through the focus F. Rule 2. A ray of light passing through the optical center passes undeviated. Rule 3. If the incident ray is passing through the focus, the refracted ray passes parallel to the principal axis. The ray diagrams for the image formation in a convex lens for different positions of an object are given. When the position of the object is at infinity, position of the image is at focus F2. Relative size of the image is highly diminished, point-sized. Nature of the image is real and inverted. When position of the object is beyond 2F1, position of the image is between F2 and 2F2. Relative size of the image is diminished. Nature of the image is real and inverted. When the position of the object is at 2F1, position of the image is at 2F2. Relative size of the image is same size. Nature of the image is real and inverted. When the position of the object is between f1 and 2f1, position of the image is beyond 2f2, relative size of the image is magnified, nature of the image is real and inverted. When position of the object is at focus f1, position of the image is at infinity, relative size of the image is infinitely large and highly magnified. Nature of the image is real and inverted. When the position of the object is between focus f1 and optical center O, position of the image is on the same side of the lens as the object. Relative size of the image is magnified. Nature of the image is virtual and erect. Sign conventions for lens. The focal length of convex lens is positive and that of concave lens is negative. Optical center of lens is taken as origin and principal axis of lens is taken as x-axis. The sign conventions for lens are similar to the sign conventions of spherical mirror. Only care should be taken to apply appropriate signs for the values of object distance, image distance, focal length, according to the type of lens, height of object, and height of image. Lens formula. The relationship between the object distance u, image distance v, and focal length f is lens formula. Here, distances should be measured according to sign conventions. The lens formula is given as 1 upon v minus 1 upon u is equal to 1 upon f. The lens formula is valid in all situations for any spherical lens. Magnification by a lens. The magnification produced by a lens is the ratio of height of the image, h2, and the height of the object, h1. Magnification is equal to height of the image upon height of the object. M is equal to h2 upon h1. Magnification produced by a lens is also related to the object distance u and image distance v. The relationship is given as magnification is equal to distance of the image upon distance of the object. M is equal to v upon u. Power of lens P. The ability of a lens to converge or diverge light rays depends on its focal length. Example, convex lens of short focal length bends the light rays through large angles by focusing them closer to the optical center. The degree of convergence of light rays achieved by convex lens is expressed in terms of power of lens. It is the reciprocal of the focal length. P is equal to 1 upon f in meters. Unit of power of lens is diopter. If focal length is expressed in meter, the power of lens is expressed in diopter. Therefore, 1 diopter is the power of a lens whose focal length is 1 meter. 1 diopter is equal to 1 upon 1 meter. The cornea forms a transparent bulge on the surface of the eyeball. The eyeball is spherical in shape with a diameter of about 2.3 centimeters. There is a transparent biconvex crystalline body located just behind the pupil. It is a lens. This crystalline lens provides fine adjustment of focal length. With the help of this adjustment, real and inverted image gets formed on the retina. Retina is the light-sensitive screen. It is a delicate membrane. It consists of large number of light-sensitive cells. These cells get activated upon illumination. They generate electrical signals. These signals are passed by optic nerves to the brain. Then, the brain interprets these signals and also processes the information in such a way that we perceive the objects as they are. The functioning of lens in human eye. The functioning of lens is very important in human eye. The eye adjusts to various object distances by changing the focal length of lens. For normal eye, in relaxed position of eye muscles, the focal length of eye lens is about 2.5 centimeters. The second focal point of eye lens is located at the retina. In this position, normal eye can form sharp images of objects located at infinite distance. At this time, the lens is thin and distant objects are clearly seen. The focal length of eye lens decreases while viewing the nearer objects and the lens becomes thick. This gives a sharp image of nearby objects on a retina. The ability of the lens of adjusting focal length is known as power of accommodation. The process of focusing the eye at different distances is called accommodation. This is brought about by a change in curvature of the elastic lens, making it thinner or fatter. But focal length of the eye lens cannot be decreased below a certain value. We cannot read the words in the book if it is held very close to our eye. The minimum distance for the normal eye at which the object can be seen clearly and distinctly without any strain on the eye is known as the distance of distinct vision. It is about 25 centimeters for normal human eye. Problems of vision and their remedies. Some people cannot see the objects clearly due to loss of power of accommodation of eye. The problems of vision are related to various reasons like weakening of ciliary muscles, change in size of eyeball, irregularities on the surface of cornea, formation of membrane over the eye lens, etc. Because of refractive defects of eye, the vision becomes blurred. There are three common refractive defects of vision. Myopia or near-sightedness. It is the defect in which a human eye can see nearby objects distinctly but is unable to see distant objects clearly. In myopia, the image of distant object is formed in front of retina. There are two possible reasons of myopia. A. As ciliary muscles do not relax sufficiently, converging power of eye lens becomes high. B. The distance between eye lens and retina increases as the eyeball is lengthened or lens is curved. A suitable concave lens can correct this defect. This lens causes light rays to diverge before they strike the lens of the eye. The power of concave lens is so chosen that it creates required divergence, and hence, after the converging action of eye lens, the image is formed on the retina. The focal length of concave lens is negative, so the power of spectacles for myopic eye is negative. Depending on the degree of defect, the power of concave lens is different for different eyes. Hypermetropia or long-sightedness. It is the defect in which human eye can see distinct objects distinctly but is unable to see nearby objects clearly. The image of near object falls behind retina. Two possible reasons of hypermetropia are: A. Weak action of ciliary muscles cause low converging power of eye lens. B. The distance between eye lens and retina decreases on account of either shortening of eyeball or flattening of lens. In this case, focal length of the eye lens is too long. This defect is corrected by using suitable convex lens. The rays coming from nearby object are first converged by convex lens and then converged by eye lens to retina. Depending upon the degree of defect in the eye, power of convex lens is different for different eyes. As the focal length of convex lens is positive, the power of spectacles for hypermetropic eye is positive. Presbyopia. It is also called as old age hypermetropia. The power of accommodation of eye usually decreases with aging. The near point of aged people recedes and they find it difficult to see nearby objects comfortably and clearly without spectacles. As ciliary muscles lose the capacity to change the focal length of eye lens, aged people experience eye lens presbyopia. Sometimes they suffer both myopia and hypermetropia, and then the person needs bifocal lens. In bifocal lens, upper part is concave lens to correct myopia and lower part is convex lens to correct hypermetropia. The concave lens is useful for distant vision and convex lens for near vision. Nowadays, refractive defects can be corrected by using contact lenses or through surgical interventions.